Welcome, my name is Philippe Verzijp and this webcast accompanies my book Data Analysis. In it, I will show you how to interpret the output of an eViews regression. When we conduct a regression in eViews, our output will look pretty much like this. Possible variations include whether or not we have the equation printed over here, which means that the coefficients are just named C1 to C4, or that the equation itself is not included and that the names of the independent variables are listed here. Of course, this does not matter one bit for the output. So let's have a closer look at that output. We want to answer three basic questions with regression. First of all, is there an impact of the independent variables on the dependent one? Do they explain any of the movements? In this case, we are using three variables, M, HML, and SNB, to explain changes in big BM3. Can't really select them properly here, but you'll get the idea. The impact of those three variables, along with a constant, are given by the coefficients. These coefficients can be pretty much any value. Also, when we look at those coefficients, we have to bear in mind that they are also multiplied by the independent variable itself. So when the coefficient for M, C2, is in this case 1.06, if we round a bit, and the coefficient C4 for S and B is minus 0.01, then we think this might be a difference of, say, a factor 100. However, should the values of S and B be, say, 1,000 times bigger as those of M, the actual impact of S and B on big BM3 will be bigger, will be larger. So we always have to look at those coefficients in relation to the average values of the independent variables. That answers the first question, is there a relation? And of course, if the coefficient would be equal to 0, there will be no relation. However, we'll seldomly find a coefficient that is exactly 0. So we also need to figure out if a coefficient, which is relatively close to that, say minus 0.011, the coefficient C4 we have here, is in fact reliable. Is that indeed different from 0, or is it just a little bit different from it due to noise, due to chance? That can happen, that will happen. To judge that, we have to look at the reliability of the coefficients. Those are expressed by the standard errors. The standard errors in themselves don't mean very much. However, you have to look at the standard errors in relation to the coefficients. And this is done by the so-called t-statistic. The t-statistic tests if the coefficients are significantly different from 0. If the coefficient is 0, you multiply something by 0, or in case of the intercept C1, you put 0 in, it has no effect. So that's what we're interested in if we want to assess if the relation is reliable. The statistic is calculated as follows. We take the coefficient minus the value under the null hypothesis, this would be 0, and divide by the standard error. So in effect, for this particular output, we would have a t-statistic equal to the coefficient divided by the standard error. Now, we see that those t-statistics differ vastly in this output. We see a large one at 87, which is very high. We see the lowest one at minus 0.72. Now, the thing is, it doesn't matter if there is a minus sign in front of it or not. That's just determined by the coefficient itself. What matters is the absolute magnitude. If the t-statistic in absolute magnitude is bigger than 2, then we have what is called a significant coefficient. Why? Well, this t-statistic can be translated into a probability. This is the p-value and is given in the last column. What does this p-value mean? This is the probability that if the coefficient would be 0, we find a number that is this big by accident. If the chance of such an accident is very low, we reject the idea that we find this value, this coefficient, by mere chance, and therefore the relation is reliable, because it's not due to chance. Now, we always have to accept a very small probability, and the customary threshold is 5%. So if the probability, the p-value, is below 5%, we reject the null hypothesis and therefore deem the coefficient to be significant. This is the case for C1, C2, and C3 over here. So in effect, it doesn't really matter too much if the t-statistic is 87 or 7. This is only relevant for how many zeros you have behind the decimal point. What is relevant, however, is if you have a t-statistic which is, of which the absolute number is smaller than 2. Then you get a probability larger than 5%. In this case, 46.7% even. This means that there is a 46.7% chance of finding a coefficient of minus 0.011 if the true value is just 0. Now, obviously, this is a very big probability, so we cannot reject the idea that this coefficient would be 0 in reality, and that we find a slightly smaller number simply due to chance. So C4 is not significant, and therefore the accompanying independent variable, called S and B, is not significant either. We could safely remove this from the model. We have 3 reliable coefficients, C1, 2, and 3, and 1, which is not reliable. However, this says little about the quality of the regression as a whole, and this is the third important question we want to answer with this output. In order to ascertain if the regression gives a good idea about the movements in the dependent variable, the thing we want to explain, big BM3, we have to look at the R squared. Now the R squared here is 94%. Given the fact that the R squared goes from 0 to 1, this sounds like a pretty good number, and it is. We have explained 94% of the variation in big BM3. However, the fact that we have explained 94% does not necessarily mean that we have a model which has good individual coefficients. As we can see, the model as a whole functions pretty well, explains a lot. However, this is not due to the S and B variable. This is just pure noise. So there's no direct relation between a high R squared and the significance of all independent variables. Vice versa, it could be possible to have 1 or 2 very significant independent variables, but a model that as a whole performs pretty poorly because there's simply a lot of noise left. So it's also possible to have low R squared going together with significant variables. But if you want to say, okay, do I understand what's going on here? In this case, you can say yes. The R squared is quite high. There's also something called the adjusted R squared, which is basically the same thing, only there is a correction made for the number of independent variables. If you add more independent variables to a regression, you will always be able to explain a little bit more. You'll always get one additional residual which you can decrease by it. So there is an additional measure, the adjusted R squared, which corrects for this. If you add a variable to your model, the R squared will always go up. The adjusted R squared may go up or go down. This concludes our discussion of the interpretation of the EFIS output.